Welcome back to the stream. Looks like we are connected again on all the usual places. Got this going out to YouTube and Twitch and Diode Zone. You put off that background job to free up some CPU. So I did a bunch of work in between streams on the storage layer. On the last stream, I was mostly rewriting the zip file loader so that we could load 64-bit zip files. I found another 64-bit related problem in the FLAC wrapper that's built into juce. It might have been easy to patch, but there were other problems with the wrapper also, and so it was, again, one of those things that was simple enough that I just ended up rewriting a very simple thing that did just what I needed it to do, instead of trying to patch juice's thing into working. So this is the latest evolution of that thing that a couple of streams ago was that shared data structure with the read-write lock. And on the last stream, I had split it up into these different pieces so that it had a kind of central database here. Then it has a reference countered object that maintains the entire index of data. That tends to stay the same, but whenever you switch input files, that'll get changed. And anyone who's still referring to the old index data can hold on to that reference as long as they need to. So we can make a nice safe transition from one data file to the next without anybody having to block or copy data or reference data that might be frayed or anything bad like that. So the index data is mostly these big arrays that get loaded in from the archive when it's first chosen. And then the actual grain data is streamed in from disk as we need it because there's just so much of it that we couldn't practically load it all into memory right away. So to get the individual grains, I decided to sort of split the processing up so that there's both the FLAC decompression and loading off the disk and kind of a batch of pre-processing, or I guess post-processing, that gets performed on each of these grains. And all of that happens on the loading thread. So the grains get loaded in from disk, decompressed, windowed. I'm getting the order wrong actually already. First they get resampled. So there's always some kind of resampling going on, just because the input is stored at a different rate than the output under all the circumstances I care about. So there's got to be some kind of resampling. I could have had a single resampler at the output and done all the synthesis at the same rate as the input. That's what I was doing at first. I decided to switch strategies to do the resampling early, which lets me do the synthesis entirely at the final rate, which seems better for quality purposes. But maybe more interestingly, it also lets me have different resampling parameters for each grain, which means I can do speed warping. And the whole idea I was trying to get to here with this particular granular synthesizer was to focus on like choosing grains rather than stretching them. So I'd be looking for something that's already got about the right pitch in a large source data set. But it's nice to have like an additional layer of control there, so I could be applying a time warp and then also look for a particular pitch and have independent control over both the pitch and the speed, which is, you know, a typical thing that you would want with a granular synthesizer anyway. So I changed the parameters around so that I can do that efficiently. And the architecture I ended up with was something where there's a cache that keeps track of loaded grain waveforms. Right now there's no strategy for deleting stuff out of the cache, so it just grows until you switch input files. But eventually that'll have a bounded size. Everything is indexed by this key, which is a collection of window parameters, that resampling speed ratio, and the actual grain number, which is an index into this table that's, well, it's per index, I guess. So this key only makes sense within the context of a single index. That's why when you ask for a grain waveform down here, this is the main entry point for actually looking up wave data. The idea is that this would be safe to call on the audio thread. It would be very inexpensive. You could call it and find out very quickly that there's no cached data and just get a null pointer and move on. But it'll also put a request out to a background thread pool to load the data. And so the key has to be qualified within an index. That's the kind of full set of parameters. So during synthesis, first you'd have to get a reference to the current index, which might change when the file is reloaded. And then once you're holding that reference to the index, you can use that to look up a waveform within the index. And this might already have it in the cache, or it might have to put up an asynchronous request for it. All right, that's most of what I got. I did end up splitting out that zip reader into a separate header here. So that was like 250 lines. That was like half of grain data as of the last stream. And now grain data is back up to about 500 lines, but now it's mostly actually reading the FLAC and sampling or resampling the resulting waveform and all that. So yeah, this big chunk of it is concerned with loading the zip file and all the parts of the zip file. This is mostly what we were working on before. Then we start this background thread pool of waveform loader threads. And we actually have these two different classes that do background jobs. There's the index loader job, which handles that zip file and JSON stuff. That runs on a kind of generic lower performance thread pool. But then the waveform loader thread is part of a dedicated thread pool just for doing this. And each thread has its own instance of a FLAC decoder and a local file object for accessing input. Has its own interpolator. Most of everything happens inside this run job function. So it's kind of switching input files as necessary, and seeking to the right location in the FLAC file after it's calculated where the data is coming from with resampling taken into account. And it's at this level we can tell the FLAC decoder, so this is libflac's API, we can tell libflac to just decode individual blocks of the file until we have enough data in our buffer. And then in this callback from libflac, we have some callbacks for reading the input file, which are just relatively thin wrappers around juce's file stream, just with our offset from the zip file reader. One performance pitfall that I wanted to really not fall into is that in Juice, their implementation of length does an entire stat system call, so it's not even just the system call overhead, it's like actually looking up the object from the file system again. So it's like both from a correctness and performance standpoint, it's just not even what I wanted. I just want to know the length of the file, right? And if you have something like fdstat, where you can stat a file and like get the metadata from a file based on a file, like a file handle, rather than a file name, that's much more appropriate for this situation. But we can still do much better because we have this thing inside of a zip file. We don't actually care what the actual file length is. We can just use the stored length of the range from the zip file header. So that avoids a bunch of both overhead and potential for 64-bit compatibility bugs. The one actual place where I did find the 64-bit compatibility bug in Juice's version of this layer was, oh yeah, in their seek function. They were just casting to integer for no apparent reason. It was really bizarre. And that's still in the latest in the latest Juice code. I don't know if I want to bother filing, like, do I feel like doing free labor on behalf of corporation, I mean, Rolly International or whoever owns them now, in order to fix a bug? I don't know that I extremely do, but if I was feeling generous, I would put in a pull request to take that int cast out of the set position in their flag seek callback. Because it works fine if you just don't do that. And EOF had basically the same problem as length, where it was relying on the actual file length unnecessarily, and so I can avoid that here too. Anyway, the main difference besides that simple 64-bit compatibility fix, the main difference between what Juice's built-in FLAC wrapper is doing and what I actually wanted to do is this is the right callback. This is what libflac calls into once it's got some decompressed data to deal with. Juice did two things I didn't really like. It did this whole separate buffering layer so that it would write this to another temporary buffer, which it would then copy out when I called read on the Juice audio format reader, which was just unnecessary. The thing that was maybe more serious is that it seemed like it was not going to be sample accurate with its seeking. I could be wrong about this, like maybe libflac is being slightly more clever about this than I can tell, but from my reading of the code and documentation, when you tell libflac to seek, it's seeking to a particular frame in the compressed data stream, not a particular sample. And when you start playing back the data stream at that point, you'll be getting frames, and those frames might not line up exactly with the sample number you asked for. So I was kind of pedantic about going through this process of matching up the sample number in the frames that we get with the sample number on the destination buffer, and I'll zero fill or skip samples if necessary. This actually does have some important other use cases though. Like, I was looking at the latency compensation for resampling, and normally the length of the data that we're reading in the source file is bounded by the width, like the maximum grain width that's reported in the header. So it'll say that, you know, here's a bunch of grain centers, and the data within this amount of time of each of those centers is guaranteed to be valid. So we shouldn't hit the beginning of the file if we take any grain and subtract that width from it. That assumption breaks, though, if we start wanting to read back even further to compensate for resampling latency, which is the thing that I wanted to try to do. I don't really know if I'm doing that correctly right now, but my attempt at that right now involves sometimes having to truncate the seek point up against 0. What's that? Yeah, so sometimes this first sample might be negative. Yeah, that's right. So resampled range is the, I don't know how much of this I feel like explaining, because I'm sure it's, I don't know. I don't know how many people are here to just hang out versus how many people are actually trying to follow along. So I don't know how much I should try to explain stuff. This window object is trying to represent like a signal processing window, like the section of the signal that I'm paying attention to. In this case, it's the grain window. So it's what portion of this, what like little grain sized portion of the audio I'm actually sampling. I'm saying little, but the windows can actually get pretty big. Some of these data sets have maximum window sizes up to like 10 seconds. That I don't know if that's actually useful, but I just wanted to experiment with it. And also, if you're doing resampling, the window size effectively ends up being divided by the resampling ratio. So if you're playing back the input at like 1/10 speed, then now you can, using the same maximum window size in the data set, you can actually load windows that are 10 times as long. So these can end up being pretty large. Yeah, I'm trying to calculate the latency of the resampler here and back up the first sample that I'm reading into the buffer to account for that, but that could end up being negative. If that's negative, that's one of the reasons we might end up zero filling in this writer callback. So anyway, the writer callback gets the decompressed data from FLAC. We do some amount of copying and some amount of zero filling and some amount of skipping here. And while we're copying, this also converts from int to floating point. It doesn't bother scaling it at all because we do a full-on normalization after applying the window function. So the scale is irrelevant here. So this is loading it into kind of a temporary buffer that is a member of this thread class. So we can access it from the FLAC callbacks, but it's not really where we want the final data to live. Once we've actually got that, we're verifying here that the progress is correct. And then there's all the post-processing steps. So I'm allocating the actual grain waveform buffer that we want, getting some pointers into and out of it, and then going channel by channel to interpolate it, and then sample by sample to window it. And then at the same time, I'm also doing the RMS level calculation. And then this is actually a third pass over the buffer to do the gain adjustment. So after all that, we've got this finished buffer of audio that has the right window function and the right sampling rate. We can just store it in RAM for some amount of time. Do the mixing back on the main thread where things are a lot more time limited. Anyway, it makes audio now. I think we can just run a debug build. Oh, I lose my connection. I think when my system's overloaded, the networked jack stuff times out and I end up losing some of my connections between computers. So the synthesis right now is kind of a total mess. Like, I think actually the next thing I need to do is put together a proper synthesizer. Right now there is not anything resembling a proper synthesizer. I'm just looping over the waveform data and swapping out the waveform data when I get new waveform data. It's not even like queuing up the loaded waveforms. So actually as I'm sweeping the mouse across, it's going through and loading a grain for every single mouse move event. So it's going to be just streaming stuff in from disk super quickly as I do this, but it's actually going to skip playing back a lot of that data because the way I've coded up this temporary playback stuff, it's only actually going to end up playing grains that have been I think the way it's set up right now, it'll only end up successfully loading a grain if the mouse is stationary for like 2 consecutive audio frames, just because it doesn't have like a queue of things that it's working on. So that's a limitation of the way I have this set up for testing right now. We've also just got it set to fairly short grains right now, just so we can hear the centers. There's definitely a glitch when it switches waveforms. None of these parameters are hooked up yet. I have some hard-coded parameters in there that right now they're a little bit weird. Anyway, these stats up here are accurate, and it's loading these files nice and fast. I'm happy with that. Like, somebody was asking in the last stream, like, oh, why are you doing all this optimization work? And that's basically why, so that you could just instantly load a 30 gigabyte source file. What are these parameters I have set? Inessa Tuco would join us, right? All this stuff, temp underscore, is just for testing. I've been trying to keep it labeled. So pick grain ends up getting called by the UI. This map panel is the UI element that's right now just drawing that image, but will provide some kind of real-time feedback for which grains are playing. So we're using this layout object that knows how to map the rectangle on the screen to grain coordinates. So that mapping is not super straightforward. I wanted to have one place that does it. think if I hardcode speed ratio to 0.5, it'll play at the regular speed. Is that right? I could just be more explicit about this. Alright, so this is get waveform from earlier. It needs to know the index and then the key within the index. So for the index, we're just using whatever's current, assuming the grain number we have still fits within that. And for the key within the index, we need the grain number, the speed ratio. The window constructor converts these parameters from the kind of friendly floating point parameters that I want to use in the UI to sample numbers. The window is a little weird. I don't know how much I want to explain it right now, but I chose a window function that I thought would be interesting. I had some graphs of it on a previous stream. It's basically just two cosines with adjustable width and with one adjustable phase. This is just a form of it where I have only one of the cosines enabled, and it's pretty thin. So I can make this full width, and we can listen to the entire grain. I think if we do that, this will listen to the entire grain at 100% speed.
Curdling Lacia integrate or blood curdling Lacia integrate pylorus single collages limb opening ukulele collages limb opening ukulele collages limb opening ukulele
Pederus Benzoy's lampshades and caps and bridesmaid supermoon cones. Bridesmaid
These are going to take a while to load.
Mutable pennants.
Pushly buckle elms flirted invitlings heave
Cane gunnels disregard aerates.
conjures promising cond obous.
Imposer non-intelligent discovered late disembarked describe
I had some printfs in there just to show when individual grains were starting and stopping. It got a little noisy though.
Transitive overriding inocular
stylus succumbing buckling lushna stylus succumbing buckling lushna stylus
custodial redeemed screamer custodial redeemed screamer
Unexcused twirls forlornly
nutrient interludes remarking nutrient darter stacks non-risky darter stacks non
Tuco's here.
darter stacks moration sin imminently and hitching sin imminently and hitching sin imminently and hitching sin imminently and hitching sin deteriorate part history 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 deteriorate landiest comma sellers denials muskiest compensate
poons friendly leash femininity unfriendly leash.
Let's set that width back to something small. Anyway, I think one of the next things I want to do is actually hook up that to the UI. Let's try setting it to something really small, actually. I don't know what the minimum useful size is actually going to be. That's too small. At least too small for single grains, maybe once it got more overlap. Oops. I hate to go. Gosh. That couldn't be good for you to chew on. Honey, honey, honey. Hey, hey, don't go back there. Are you gonna stand on everything now? Zuko. I can't see anything. Oh, oh. Oh. So was that Control C? Zuko. Okay, fine. Just unplug the keyboard. Zuko, is this all you want to do? Okay, cat break. Oh, you're moving right when I tried to move the camera. I'm coming right back, honey. You wanna sit on my mouse now? Maybe Tuco's choosing where this stream goes. Where's he going? I also made some just small quality of life improvements in the UI. Like, I'm actually saving the size of the window now, and I'm saving the list of recent files. It makes it much more convenient to actually just open it up and have it ready to go each time. So mostly at this stage here, building a MIDI synthesizer. I wasn't really sure how to map this thing that I'm doing to Juice the synthesizer. In particular, I wasn't sure where the boundary should be between like the processing of one like instrument voice versus one grain. Like, should I actually try to break up each MIDI note into a bunch of grains that all happen independently? I think the answer to that is no. Like, I don't really see any benefit to that, and it potentially makes both the design and the implementation more complicated and lower performance. I think it makes sense to think about, well, I think it makes sense broadly to use the synthesizer framework that Juice has, and they break up the object model into sounds and voices. Where the synthesizer itself is kind of a general purpose thing that you can use without modifying, and then you can load the sounds and the voices into it. The sounds, I think, are meant to represent some particular like set of parameters that you might want to use as like an instance of a thing that you're playing. So they have an example here actually where the sound class basically is a no-op. Like they're not storing any useful information in here. It just doesn't make it super easy to tell how you would use it. I think the documentation makes it seem like this would be a a natural match to like a single sample if you were doing a sampled synthesizer. So maybe the synthesizer sound would be a chunk of waveform data, and it has, you know, some range of MIDI notes that it applies to. And then when you play it, you can choose to stretch that waveform data, play it back however you want. That seems to make sense. I think maybe another way to look at this would be that the sound is like a collection of parameters that a voice can use to generate audio. And I think in my case, I want this to be maybe a single set of windowing parameters, so the window doesn't change for the duration of one sound. And then it would represent whatever information is necessary to generate a series of grains that map to like one MIDI note. So one way to represent that might just be a copy of like all the knobs in the UI. Like if there's a, you know, if there's a grain modulator knob, then that just controls how the sound responds to MIDI events to generate a sequence of grains. It's pretty simple, and I think it might also be the most efficient way to do it, because I don't know that I even want to ever actually have to store a list of grains, right? Because that might be very long. It might be never ending if you're just holding down a note that's randomly playing different grains. So I think I really just want to think about the sound as a set of parameters and an object that can be like an iterator that produces overlapping grains. So it'll produce a series, like a train of overlapping grains that all have the same window. They could have different grain numbers, different locations in time. Like in the current model I've got, I guess they would be regularly spaced also, but that doesn't seem like a super important requirement. I think the most important requirement is that the window stays the same, and the grains form like a strict sequence. So like they come in order. I can't find out about a grain that should be played while something else has already been playing. So there has to be a way for me to kind of look ahead and get a list of which grains should be loaded, and then start those loading as soon as possible. And then maybe delay that entire sequence of grains until the first chunk of waveform data is actually loaded. 2 goes back. So yeah, I think what I need to do is map synthesizer sound to basically a set of parameters. And then synthesizer voice would be a thing that can actually keep track of a queue of overlapping grains that are all being rendered. But, you know, with a single MIDI note. And for MIDI polyphony, it would have multiple voices running concurrently. Oh, thanks for the tip. $5 from Joseph on YouTube. Thank you. The other bit of architecture I wanted to try to work out that's related to this is how do I actually connect the parameters in my data model to something that gets into the synthesizer proper. In some of the simpler examples in Juice, they actually just have you read from the value object in the value tree. And I think as long as you already have a reference to the value that you got while the UI threads lock was held, and you don't write that reference, I think it's safe to use those references on the audio thread. So we could do it that way. There's still the issue of like, do you want the current thing or the version of the thing when the note started playing? And in most cases, you don't necessarily want the current thing. You want to capture it when the note starts and then avoid changing it abruptly. And the synthesizer sound objects are reference counted, and it seems like one way to deal with this elegantly-ish would be to have a change callback on the data model for all the parameters that we need to incorporate into the synthesizer. And then anytime any of those change, we allocate a new synthesizer and make that current, and any voices that are still using the old one can continue to reference it, but it won't be used to start any new voices. That seems pretty straightforward and unproblematic. And then I guess I said I don't want to have like a queue of actual grains, because that might be infinite, but I guess I do want a limited size FIFO queue of grains in each voice. So the voice would look ahead to some amount, figure out what grains it actually needs to play, which you know, that might change also. Like, what happens if okay, so I guess one way to think about this is that this FIFO queue I'm thinking of actually defines the latency for things like MIDI pitch wheel events to control the grain modulation. So we'd want to kind of pre-prepare grains a certain amount in the future and get them started loading into the cache. And that probably shouldn't be like a fixed number of grains. That should probably be like an amount of time that we look ahead. It should probably be like a defined event latency, and we try to prefetch grains through there. I don't know if I need audio source. You okay, boy? Yeah, I was curious if there was anything special in Juice for connecting synthesizers to an audio processor. Looks like that is what they're doing here, and it's just pretty straightforward. Oh, so files. I've got a bunch of kind of small files for the UI still. An audio processor is mostly about the data model at this point. I've been assuming most of these UI panels will end up getting somewhat complicated, so I don't really worry about them being a bunch of annoying tiny files at this point. The map panel is already somewhat complicated because of that background image renderer, and it's only going to get more so. The param panel is probably always going to be pretty tiny, though it's tempting to merge that one into audio processor editor. Same with data panel, really. Window panel is definitely going to get more complicated right now. There's nothing in there, but this is another one that's going to be drawing a graph that you can interact with. I don't know, let's not worry about consolidating files, but I think, want to make a new set of files for synthesizer related stuff. Probably with the synthesizer sound and voice in the same file. It's tempting to just call this grainsynth.h in CPP. Oh, Tuco's gonna make me sneeze. Maybe this is too small. That's a big step up, though. Somebody from chat is wondering if I have opinions about protocol buffers as a format. I don't know, they seem fine. I don't know why I would have opinions on a data format, really. It's one of many things you could use to do many different jobs. I mean, it's like one of those things that is very convenient if you've already got all the tooling set up, but it's a little bit annoying to kind of first jump into because you've got to like learn the definition language and figure out the tooling for that for the language that you're working in and whatever. And it's certainly more complicated than something like JSON, probably less complicated than XML, but you know, for good reason. Like there's a lot of stuff that JSON is just horrifically bad for, and it's usually not relevant for like embedded contexts or places where space efficiency is really important. So like, I don't know, Google's got a lot of good reasons to use protocol buffers. Other people have got a lot of good reasons to use them, but I don't have a lot of reasons to have strong feelings about computer file formats at the moment. I don't know if synthesizer voice is going to have any of its own API. Like it's mostly responding to MIDI events via the synthesizer. What about the sound? I'm going to attach the index. It does seem like the sound wants to have an actual pointer, like a ref counted pointer to the index. So when we finish loading an index, the synthesizer would actually take a reference to it as soon as it could. Hold that reference until the voices are still using it. Yeah, that's where I'm getting at. What I'm getting at is that this grain synth sound might be like, that might be like the main place I actually want to get together the parameters that the synthesizer needs. Like that constructor is probably where I'm taking an index pointer and figuring out okay, where's the sample rate known? Sample rate probably has to go into the constructor of Yeah, I think just anytime any of that changes, I rebuild the parameter set here. Okay, so we've got window parameters. Grain rate will be separate. I'm gonna top off my coffee. Maybe it makes sense for this to be a pointer. The thing I like, I mean, so it's probably already going to be a pointer at this point, but passing it in as a reference is a good way to document that there's no sensible interpretation of null there. I'm just getting cranky because this, like, the simplest way to do this involves passing a bunch of arguments to this, and maybe I end up wanting like something a bit more stateful. Actually, how do we feel about mutability on these synthesizer sounds? I mean, the way they do it for sampler sound is just have a constructor with a bunch of arguments. Oh, but the envelope is mutable. I feel like I do actually want to have a little structure that just has these parameters in a somewhat different form. This window object is like the internal representation of a window after it's been converted to the right sample rate and everything. I think I do actually want that conversion to happen in the constructor, so this would actually be dealing with something that's basically just a bunch of floats that match up with these parameters. I mean, I could also give it the value tree directly, but I don't think I want it to have to know about the value tree. I think I'd rather have the audio processor deal with getting data into and out of that format. Somebody spotted my typo, thanks. I'm sure I would have noticed that before too long, but I don't want to offend your delicate sensibilities out there. Could I also use this as our central place to store the default parameters, maybe? I don't know if I care about that. This does not need double precision, but I think it's double in all the juice APIs, so I think I might just avoid the conversion. Yeah. Let's just call this sample rate. I'm overthinking whether or not I want this pointer to be part of the params or not. I think I don't. I think the params should be plain old data. Right, that might end up having reasons to diverge from the UI visible parameters, but this is for the most part just the UI visible parameters at this point. And this will use the data in the index to figure out some of the specific versions of that, like the window sample, or the like the window in input samples, or in the window in output samples, and then the ratio between input samples and output samples. The actual sample rate will depend on the sample rate and the speed warp. Let's define these. I think I store the original params, and then I also store the window, even though there's some duplication there. all these functions with equal 0 are pure virtual functions. So virtual means we can override them in subclasses, and pure virtual means they have no default implementation. So by default, if you were to instance this, or if you were to create a class that is a subclass of synthesizer voice, it would not compile unless you define all of these. Or rather, it would let you define that class. It would not let you create an instance of it if you didn't have all of these defined. Like in juice, they had a bunch of these defined as equal 0, and this is an object you can use for purposes like this, but you can't actually create an instance of synthesizer voice. It'll tell you that it's missing implementations for those functions. Cool. So we have rendering blocks and inputs. And the synthesizer will do most of the work in actually getting us from MIDI to this point, which is nice. I'm being stingy with the variable names here. Do actually need to initialize the window here. Let's explicitly calculate the speed ratio first. Okay, so this is input samples per output sample. Index just says sample rate, there's a float. And then I want to multiply that by speed warp. I don't know that there's any reason for speed warp and sample rate to be separate parameters, but I think I just want to do the thing that makes this as kind of unsurprising as possible. Now this can divide the window size by speed ratio, and then deal with the other parameters. Yeah, okay. I think in Juice's example, they suggested you just use RTTI for this. Oh, is it cool that this is just a regular pointer? I need to look up the lifetime for that. The synthesizer seemed like it was using smart pointers and reference counting. Sounds everywhere, so I don't know what this is about. I'm going to worry about the contents of most of these later after I get the infrastructure set up to route the audio through this whole mess. Render next block. Cool. That looks like a nice, cozy spot to write some synthesizer code once I get more of the environment set up. There's a lot of stuff in here I might want to hook up later to make this nicer to use. Like, I think this program select stuff is used for switching sound presets. And it might be interesting to wire that up to the recently used list in the file picker, so that you could flip between those from your DAW software. Okay, let's get rid of some of this temporary stuff. It's tempting to disable that output sample rate entirely. I'm just gonna remove this mouse move thing entirely. I don't think we need that. It was very handy for debugging though. I might just put a printf here for temporary purposes. Okay, so now audio processor can refer to grain synth. Okay, so we have one instance of the juice synthesizer. We'll have some number of voices, you know, like 64 or whatever we want. And those can just, I think, anonymously live inside the synthesizer for a while. I still need to check on the lifetimes for those objects. And then the sound, this will be a reference to the latest sound that we have for the current parameters, but then we might have references to old versions of this in various places. Oh, it's Yuko. It's a little weird that they would be using a raw pointer for this instead of either a reference or a smart pointer. Let's just read the code to see what it's doing. Voices are not reference counted, are they? I think I misspoke about that. Yeah. Voices are just owned by the synthesizer. The remaining wrinkle in this design I'm thinking about is that in Juice's model here, the sample rate is a property of the voice, and I think in my model it makes more sense if that's part of the sound. Like if you were to change the output sample rate, that would mean getting all new data from the cache. It's part of that whole category of parameters. So can I just basically ignore the synthesizer's notion of what the current sample rate is? I might just use the synthesizer to keep track of the sample rate so that I don't have to store it as a separate number here. And use that to generate the sounds. How did the camera read? This is getting a little warm in here. Just see if this compiles and clean it up a little, but This should instantiate the synthesizer. It'll have it keep track of our output sample rate. It'll add a bunch of voices. They won't do anything yet. Oh, can I go ahead and hook up process audio block? So yeah, I'll try to hook this up. I think the next major thing to add is a function that regenerates our notion of the latest sound, updating this pointer. And we'll call that when the sample rate changes or when any of the input parameters change. I guess we have to always clear the buffer. Oh. Okay, synthesizer and color are two words that I just need to avoid. There's no synthesizer support, just synthesizer support. Cool. Running, but not producing any output. I think there are a few different ways in Juice to make a linkage between one of these parameters in your state tree and just a plain old floating point number. It's a little less efficient than we could be doing it, but I think I might just attach a listener to the entire state tree. The penalty for unnecessarily regenerating this sound object is pretty low. If we do end up, for example, replacing it with one that has the same window parameters, then we still end up with the same cache hits, and I don't think anybody cares that this is a new instance of grain sound. Yeah, this will get us a value tree property changed callback. If this replace state places the attached listeners. Just let this camera cool off. Oh, that's not in this. That's right. There's another layer around this. The state thing is not actually a value tree. It's an audio processor mumble value tree. Value tree state. Okay, this gives us slightly different listeners. I mean, I think these are just convenient functions that wrap around the other listeners. I think that replaces all of our listeners. Parameter adapters. Is this somebody's backwards compatibility feature? Okay. I don't know how much to care about this audio processor value tree state class. I might just kind of look past it and use its underlying value tree. That means we do need to set it inside attach state. So attach state runs after we replace the entire state tree through loading from disk or up here during initialization. I don't think we need to get all the way to call it update state or update sound from state during initialization. So before we get the first output sample rate, that'll be pretty meaningless. I guess I don't need to keep track of the sound myself. I should be tracking that inside synth. And so does it do its own locking there? The issue here is that synthesizer does need to be in charge of some data that's shared between threads. Like, it's mostly invoked by the audio thread, but then we have these property changes coming in sometimes. We might have the UI thread starting notes, that kind of thing. It looks like they have a lock that will serialize changes, but won't contend with the audio thread. I think that's fine. We're going to treat these sounds as immutable after they're added to the synthesizer. I don't know if there's a great way to just swap out a new sound in, though. I think we'll have to do add sound followed by remove sound. It's almost where I need it to be. Assuming this seems to be getting called at all the right places. Yeah, updating sound monitor. We need this when the index changes too. There's a status, there's like a loading status value that's using the same data structures as the state tree, but it isn't actually part of the state tree. But we can add a listener to that also. Yeah, I think we want to do the exact same thing here. Okay, so this will create a link between grain data status and grain data's internal status value. And then attach a listener, which we need to implement. Okay, we should get this updating sound pointer message now when we change input files. There you go. Whoa, just a sec. Cool. So we do have several calls to that, which is as expected since we're regenerating this sound pointer for every change and there are multiple changes happening. But that's fine. It's inexpensive to regenerate that. I just want to make sure that it's done at the right times. Okay. Oh, to go. Hey. Oh, he is purring. Oh. gosh, when I have the mic turned up to catch all the purrs, one drink of coffee is like a major hydrological event. And there's a comment that the cat is all the keyboard I need. I agree. I think I'd be better off if I could take a break every time Tuco wants me to take one. Well, maybe I could wrap up the stream pretty soon. This is probably the nicest stopping point I'm gonna get for a little while. Maybe before wrapping up, I could try out some of the databases that it recently finished generating. Oops. It's safe to plug the keyboard back in right now. I guess I can't really do that easily right now because I don't have audio output. Maybe I have to save that until audio is unbroken, or revert to some code from the beginning of the stream. So this big 27 gigabyte one finished like yesterday. I guess late this morning, early this morning. I've got some that I've got like small versions of right now, and I'm working on bigger versions of. Like I've got Bob Ross episodes and Boards of Canada music. I wanted to just throw a few different things in here just to see what kinds of effects I can get. This seems like a good stopping point though. Tuco really wants my attention. Let's keep the keyboard unplugged. I still feel like this project is a bit of a mess, but it's nice having it really quickly load these input files at least. All right, I'll see everyone next time.